Welcome to lecture 17 of this course. In the previous lecture, we discussed the preliminary concepts, term unification, substitution, most general unifier MGU, and the unification algorithm related to the principal type algorithm. In today's lecture, we are going to discuss the principal type algorithm. Principal type means general type. The general type of the identity function is A arrow A. Now, A arrow A is also a type of the identity function. However, it is not general since it is a substitution instance of A arrow A. So, if you substitute A with A arrow A, we get this one. So, we say A arrow A is general type of identity function. Now, general type can also be viewed as one having the simplest structure, one with the least constraints. So, here for example, the first one says it is a function with A arrow A, there is a type variable A to another type variable A. Now, this one says it is a function from its domain will be a function, the range will also be a function, but this is more constrained than the other one. So, we say this has a simpler structure than this one, and in fact this is the simplest. So, if the structure is the simplest, that is called the general type or the principal type of a function. Now, when you are studying principal type algorithm, our goal is given a lambda term m, find the principal type of m if one exists. So, there are two cases, one is m is typable and the other is m is not typable. If m is typable, the principal type algorithm should give the principal deduction. So, that is written as delta m for m. On the other hand, if it is not typable, the principal type algorithm should give a correct statement that there does not exist any type for m. So, this is important. It should give a correct statement that there does not exist, that is indeed, that means indeed that there is no type for m. So, if we move toward the design of the principal type algorithm, its structure will be like this. A lambda term m is the input to the algorithm, and the idea is to recursively apply the algorithm to subterms of m. So, we look for the possible structures of m. So, we know that the terms of lambda calculus, there are essentially three things. One is a variable, another is an abstraction, another is an application. So, we see which structure is matches. So, first one, if it is a variable. So, if m is of the form variable, then the principal type of m is the principal type of x, and then we can say that we can assign a to x. So, a is a type variable. So, x as type a will be the principal type of m, and this is the base case of the recursion. So, then a slightly more complicated formula would be, say the structure would be, it will be abstraction lambda x dot p. So, in order to find this principal type of this m, we first need principal type of p. Once we have the principal type of p, then we apply arrow introduction, we know the rule of arrow I, to obtain the principal type of m. So, if the principal type of p is rho and x has type sigma, then arrow I will give us principal type of m to be sigma arrow rho, because arrow I introduces lambda x has type sigma, so it will be a mapping from sigma to rho. So, this is the second case, and then we have the application case, that means it is of the form PQ. And now, in order to find this principal type of m, we first find the principal types of these P and Q. Now, we know that arrow E, it is of the form arrow E to be applied. So, P should be of the form sigma, rho arrow sigma, and Q is some tau. Then, we check if there exists a unifier for rho t. That means, if it is unifiable, then this rho and tau should unify. That means, there is a substitution that makes them look syntactically identical. If that be the case, then we apply the substitution onto these things as we discussed in the previous lecture, and as a result we are going to get sigma star. Sigma star means when S is applied to sigma, let S be the unifier, the substitution that unifies these two. So, S of sigma will be equal to S of tau, and this S of sigma is actually sigma star. So, this is obtained by arrow E. If that is not the case, that means we are not able to find a unifier, then we say that m is not typable. Thus, what we see that in essence, that finding the principal type of m, this was our problem. This problem then reduces to the problem of finding the unifier of rho t, rho tau. However, we note that the application case is a bit involved due to the unification. Others are straightforward. So we will discuss this in more detail when we present the actual algorithm. Now we need certain definitions before we can proceed, and these definitions and result are from chapters 2 and 3 of Basic Simple Type Theory by Roger Hindley. So let gamma be a type context. So we say if and only if there is a TL lambda deduction of a formula M has type tau in a context gamma prime, where gamma prime is a subset of gamma. We say that M has type tau is deducible in TL lambda. So this is the notation here. So there is a notation we note here. First we note this represents a formula that is a triple, the context, the lambda term and the tau. This notation, this means that this type is deducible, that there is a deduction, that means there exists a deduction for M has type tau in a context gamma. And this is traditionally, this symbol is called the deducible. This symbol in logic is called deducible. So this in TL lambda there is a deduction of M as tau. This is represented in this notation, and this is different from this one. This is just saying this is a formula, and this is saying that there exists a deduction that M has type tau in a context gamma. And when the context is empty, that means it is an empty set, we say M has type tau in TL lambda, or we simply say when TL lambda, the context TL lambda is understood, we will simply say M has type tau. Now we define the principal type, but when TL lambda, a principal type, or we are always going to write PT of a term M is a type tau such that M has type tau in some context gamma is deducible, and 2, if M has type sigma is deducible from some context gamma prime and sigma, then sigma is an instance of tau. Sigma is an instance of tau. If that be the case, then we say that tau is the principal type of M. Likewise, we can define what is called a principal pair. Now, principal pair of a term M is a pair that is a context and the type gamma and tau such that the formula, that is M has type tau in the context gamma, is TL lambda deducible, and every other TL lambda deducible formula is an instance of this gamma in the context gamma M has type tau. So this is the similar way we are extending this definition to principal type to principal pair. That means one will be an instance of the other. If that be the case, we call it a principal pair. Now we proceed to the definition of principal deduction. A principal deduction of a term M is a deduction delta of a formula that M has type tau in the context gamma, such that every other deduction whose conclusion subject is M is an instance of delta. So that means if you recall that when we are doing a deduction, that means here we had this M, we are trying to say M as some type sigma or sigma prime, and this M, that other deduction, this should be the conclusion subject. That means if we are doing a deduction for some other deduction, then with the subject this, then that will be an instance of delta. If that be the case, we say delta is the principal deduction of M. Now we take up on the principal type theorem. Now it says that each typeable term has a principal deduction and a principal type in TL lambda. There is an algorithm to decide whether a given lambda term M is typeable in TL lambda. And if the answer is yes, we will produce a principal deduction and a principal type for M. So that means what we have obtained from this theorem is that given a lambda term M, there is a, if it is each lambda typeable, if it is typeable, then there will be a principal type, that is the most general type, and correspondingly there will be a principal deduction. This is what we are going to obtain. And then there is an algorithm which is going to return this principal type and the principal deduction for M. Okay, now we present the principal type algorithm. So this is from chapter 3 of Basic Simple Type Theory book, and this was suggested by Roger Hindley in 1969. So it takes as input an untyped lambda term M, and if M is typeable, it returns the principal deduction. We write delta M for M, else a correct statement that M is not typeable. So we break up this algorithm into different cases as we discussed informally. So the case 1 we say when M is a variable. So then the principal deduction will be just X has type A and this is the just the deduction. So then this is the axioms. If you remember in TA lambda we have an axioms for every variable and every type. So this is the variable, we say this is a type variable and we say X has A. This is the context, then the type of X will be A. So this is the principal deduction. Now case 2 is abstraction. So we have M is lambda X dot P and X is a free variable occurring in P. And let the free variables be X, X1 to Xt. Now we apply the algorithm to P, and if the P is if we find that P is not typeable, then M will also not be typeable. Now suppose P has a type. That means P the principal deduction of P will be delta P, and the conclusion will be of this form that X has type alpha. These are the term variables, and we associate the type variables types with it. So it will be all of them we are associating some type that has been obtained as a conclusion, and for some types alpha, alpha 1 to beta. Now we will apply arrow I main because it is in the free variable of P. So arrow I main will give us that lambda X dot P has type alpha arrow beta. So this is the principal deduction of lambda X dot P when X is a free variable in P. So this is straightforward because it is coming from arrow I main. The only thing is that the conclusion will have this all the type term variables have been assigned some types, and P has type beta in this context. Then we are going to use arrow I main and we are going to get lambda X dot P has type. Case 3 is also an abstraction, but X is not a free variable in P. That means X does not occur inside P, in the body of P. That means now free variables will be excluding X, so is X1 to Xt. As before, we are going to apply the algorithm to P and check if P is typeable. If it is not, then M is also not typeable. If P is typeable, again as before, the principal deduction be delta P. Now the conclusion, we will have assignments to all these term variables. So we have xm alpha 1 and so on, st alpha 2, and P has type beta for some types alpha 1, alpha t and beta. Now we choose a new type variable D not in delta P. That means this type variable should not occur in this. That means it is not any one of these alpha is, it is not beta, and we say let X has type D. Now we will do the discharge vacuously. The rule, there are two rules if you remember. One was arrow I main and arrow I vacuously. That means we are discharging X vacuously. If that be the case, now lambda xp will have type D arrow beta. So we have seen the abstraction part. Now we consider the application part. Now form of M is P, Q. So we apply the algorithm to P and Q. If any one of them is not typeable, then M will also be not typeable. That means both P and Q should be typeable. If that be the case, let the principal deductions be delta P and delta Q. Now we ensure that in the deductions, they have no common type variables. And if indeed there is a common type variable, we will rename it if required. Now let the free term variables that are common to P and Q be W1 to WR, if any. That means R will be in general greater than equal to 0. If there are no term variables common, then we write it will be empty set. Otherwise, we have something W1, W2, so some are. And there are these other free term variables that are not common. So we have these UIs. In delta P, there are some UIs, and in delta Q, we have the VIs, V1 to Vk. So these are the types that we have. The context then is all these term variables of free term variables of P, these are included here. Free term variables are Q are included here, and among them these are the things that are common. These are the common to both P and Q. But then they need not have the same types. here it is phi 1, here it is phi r, here it is theta 1, theta r, because these are independent. So we have obtained this. Now P has type rho arrow sigma and Q has type rho prime. Now what we have to do? We have to apply the unification algorithm. That means this part and this part we have to consider, and this part and this part we have to consider. So that means we have to apply the unification algorithm to the pair of sequences. This will be the sequence 1, phi 1 phi r to rho, theta 1 theta r to rho prime. Suppose there is no unifier for this, then M is not typeable. Otherwise, let U be the most general unifier for these two pairs of sequences. Now we have to apply these two, that U will be applied to all of these. So we create a substitution instance of them. So as a result, U of rho will be equal to U of rho prime, and the answer will be U of sigma. So this PQ type will be U of sigma. So this is the idea. But now we have a difficult situation here. Earlier when we studied most general unifier or the unification algorithm, we said we are doing a pair of types, say rho and tau. Rho and tau we were doing unification, and the unification algorithm was applied to this pair of types, and it would return at MGU if a unifier exists, otherwise it will say no. Now we have a sequence, pair of sequences. Now this, the algorithm we cannot fit directly. So the idea here then, we have to give a definition of how to convert these sequences into our original form. So the idea here is, if we have two sequences, rho 1 rho n and tau 1 tau n, so introduce a new variable b that is not occurring in any of these types. Then we create a type rho star, which is rho 1 rho 2 all the way rho n to b. So now it is one type, arrow type, you can say it's the arrow type. Say n is 2, so it will be rho 1 arrow rho 2 arrow b. And similarly tau star will be tau 1 arrow tau 2 arrow b. They are of the same length. It has to be of the same length, otherwise unification will fail. Now what we have, original algorithm, we can fit this, and we are saying that look, we have now again two types, we have to unify it, and now the unification, then the given pair of sequences is unified by a substitution S if and only if this pair rho star sigma tau star is unified by S restricted. So the idea is we have restricted the substitution to the variables in this. Whatever variables that are occurring in this, we have to restrict it, and then we can proceed as before. So we take a small example. So we say there, so rho consists of two elements, A arrow B and C, and this is DE. So this is first transformed to A arrow B arrow C arrow F, and the other one is D arrow E arrow F. F is the new type variable we have introduced here. Now we will just do D will be replaced with A arrow B and E is replaced with C. So we get a syntactically identical type, and that is the unifier for these two sequences. So now we illustrate the working of the principal type algorithm. So we consider some examples. So first let us consider the identity function lambda x dot x. So M is lambda x dot x. The idea is that if it is x, if M was x, then we will do, this is the smallest thing possible. Now it is an abstraction, so that means there is another sub term. So we do case, so this falls in the case 2, it is abstraction. Now here this part we are extracting the sub term, this will be case 1. This is the simplest thing that is possible. So we have x. So here P is x. So our original problem we have categorized into case 2, then the sub term is x, which is P, and there case 1 is applicable, and now case 1 says that the principal deduction will be in the context x has type A, the type of x is A. Once this is done, so here x in the body x is occurring, so x is a free variable in this P, so that means case 2 will be applicable, so it will be arrow I main, so it will be arrow I main, so in that case it will be, this one will be lambda x will have type A arrow A. And we now obtain that From the algorithm we obtained that the principal type or the general type of the identity function is indeed arrow A. Now we take the other example. Now this involves abstraction and application. So here we see it is form is lambda x, lambda y, xy. That means the first this part it has subterm this. This is a subterm of this. This is our p. Now p is lambda y dot xy. That means p subterm is this. We cannot go any further. So this is the point where we have to stop. That means xy is now an application. Now it is case 4. This part was case 1, case 2. This is again case 2. Now we have to do case 4 here, xy. Now for the subterm xy, we see it is an application, mn, sort of a structure. So here p is x and q is y. So case 1 we have to apply and we have to say that x is of type A arrow B. It has to be of row arrow sigma and that form, it is arrow type. So we say x has type A arrow B, x has type A arrow B. In this context, A arrow B, this will be the deduction of delta p, and that deduction for q will be y has type C. This is the context and y has type tau. So we have this form sigma arrow tau, and this is some sigma prime we have done. Now we have to see the free variables that are there in this. So free term variables, where the free variable is x, here the free variable is y, and also the type variables, all we have no common type variables are there. A, B are the type variables in P, C is a type variable in Q, nothing is common. Then we check the term variables. Now term variables x and y, they are different. So then what we have to do, we have to just match A and C. That means to unify this pair AC, because we have no free common term variable. Now this is very straightforward. So we either replace A with C or we replace C with A. So we replace C with A. So now C with A, if we replace, this part will become A, this is A by the substitution, and now A and A matches. So when we do arrow E, we are going to get the type as B. So type of PQ is B in the context. Now Y has type A and X has type A arrow B. So now we apply case 2. So this will be case 2. So case 2 we have to apply this xy, this whole term say R. So this will be then A arrow B. Lambda y has type A, so it will be A arrow B. Now again we have to put it, this part we have obtained. This part is of type A arrow B. Now again lambda x is there, x is A arrow B. So the type of M is A arrow B arrow. This is the term. So that means if I have that x is of type A arrow B, type argument input is A, B, and A is taking returning B. So that's the idea of PT algorithm for this example. Now we take the third example. Now principal type of M is lambda x dot xx. Now as before, it is of the same thing, lambda x dot x, this is case 2, and now this is the subterm, this will be case 4. So this part we have to work on, this is application. So here P is x and Q is also x. So principal deduction of P will be as before A arrow B, and this will be the principal. X has A arrow B, and in this context x will be of type A arrow B. And C in the context is x has C and x has type C. Now we have to unify these two. Now we can proceed and say that now what we have to first see that in the free variable, the type variables are all distinct, but free variable x is a common to both of them. X is common. X is a common free term variable. Then as per the rule, we have to unify the sequence A arrow B A, this part and this, and C and C. This we have to, the pair of sequence we have to unify. That means we have to transform this by that rule, A arrow B arrow A arrow D, new variable we have introduced, and here will be C arrow D. So these two types now we have to unify. This is the type. So you see there are 1, 2, 3 or 1, 2, 3. Now replace C with A arrow B. That means this part will match. Now this becomes A arrow B. C part becomes A arrow B. A and then A arrow B we have to match. This part and A arrow B we have to now match. Now A and ARO beta, they are not equivalent for any beta. Hence, A and ARO B, they are not equivalent, because one is a function type involving A, another is just a type variable A. So, these two, A and ARO B, they are not unifiable. Hence, this one not unifiable, and hence we have M is also not unifiable, because XX is not unifiable, and hence then lambda x dot x is also not unifiable. Thus, we say conclude that M is not typeable. So, what then we obtained is, by the algorithm, we know this expression is our self-application SA, and we have proved that by arrow E, but arrow E also we have proved it is not typeable. So, the algorithm, indeed it is giving the correct statement that M is not typeable. Remember that if it is typeable, it is going to give the principal deduction. If it is not typeable, it is going to give a correct statement that M is not typeable. Here it is we know that it is not typeable, and algorithm has also giving the answer no, and the instance that why it is no, it is showing that look, this sequence cannot be unified. That means we cannot unify A and ARO B, and that is the reason why we cannot give a type to this. So, from the working of this principal type algorithm, it is now easy to see that self-application SA, if SA is a subterm of M, then N is not typeable. If we have a term M and SA is occurring there, then it is not. That means if I have big omega, so big omega is SA, and we know beta reduction will lead to SA only, infinitely many times this will come. So, that means obviously we know SA is not typeable, then SA will also not be typeable. Now, we can easily appreciate the importance of restricted lambda terms. Recall that in the previous lectures we studied restricted lambda terms like lambda I term, lambda BCK lambda term, and BCI lambda term. Now, we see that in SA we have this x variable parameter x is occurring 2 times, but BCK says it is at most 1. That means SA is not a BCK lambda term, and a BCI lambda term is one that is both BCK and lambda I term. So, hence it is not a BCI lambda term. BCI lambda term means it is non-cancelling and non-duplicating. So, here it is duplicating. So, SA is not a BCI lambda term as well. And earlier also we have studied a theorem that every BCK lambda term is typeable. That means if I take a term that is in this class BCK, that means either B combinator or a C combinator or a K combinator, or from this we obtained some terms that is in the class, they are bound to be typeable. And if that term we feed into our algorithm, it will give us the principal deduction and the principal type. Okay, now we discuss the principal type algorithms, history about this algorithm. This algorithm, often called algorithm W, was introduced by Hindley in his famous paper, The Principal Type Scheme of an Object in Combinatory Logic, in 1969. It appeared in the Transactions of American Mathematical Society. The principal type or principal type scheme is the most general type, such that all other types can be obtained by instantiating it. And in this paper, Hindley proved that every typeable lambda term has a unique principal type scheme. That means the type that we have obtained, we are calling it that type, it is returning a principal type, it is a unique. That was proved by Hindley in that paper. So, this provided the foundation for type inferencing in functional programming languages like Haskell, ML, OCaml. Later in 1978, based on this result of Hindley, Robin Millar developed algorithm W, and that is a practical type inferencing algorithm for type reconstruction in ML. In his paper, A Theory of Type Polymorphism in Programming, in the Journal of Computer and System Sciences. And the language ML was also developed, invented by Millar and his colleagues, and ML is actually a class of languages. So OCaml is also part of that. OCaml came from ML. So, the PT algorithm is also called the Hindley-Millar type inferencing algorithm. And there is an interesting historical comment on the origin of this sort of algorithms. It is a series of algorithms. So, Hindley traces is back to the 1920s. So, you are requested to take a look on this historical comment. So, let us summarize today's discussion. We have discuss the principal type algorithm, and we have seen that some restrictions, what is the influence of the restricted lambda terms that we earlier studied has this on this. For if you consider the restricted lambda terms, they will be typeable. So that is one class that we have earlier discussed. So you are requested to please see chapter 3 of this book. So with this we stop. Thank you for your kind attention.